Welcome to iLecture Online, and now let's take a look and see what clever techniques very intelligent and smart mathematicians came up with more than 1,000 years after Archimedes came up with his clever technique of using circles and inscribe and circumscribe polygons. What we'd started doing here is starting to notice that there were certain patterns that we can come up with that were exemplary of calculations we could do geometrically. And so we can then say, wow, we can then go ahead and turn it into an infinite series. We can actually come up with a really accurate method. So people started coming up with infinite series. First of all, Francois Viette in 1593 came up with this very clever way of calculating pi. It was equal to 2 times 2 divided by the square root of 2 times 2 divided by the square root of 2 plus the square root of 2 plus 2 times the square root of 2 plus the square root of 2 plus the square root of 2 and so forth. And you can see the pattern. And just to make it easier, I went ahead and started calculating this. So here the denominators are equal to these 4 numbers. Notice that the denominator tends to converge to 2 as you go farther and farther out. And so then eventually you start multiplying by numbers very close to 1, and that no longer changes the value. But let's take a look and see what that is equal to. So here we can come up with 2 times 2 times 2 times 2, which is 16, divided by, and let me put on my glasses so I don't make mistakes. So divided by 1.414, divided by 1.848, divided by 1.962, and that ends up being 3.12. So this is equal to 3.12. Notice that it's actually very close to the actual value for pi. Not a bad estimate, with only going 3 terms like that. Now here's another series that was made by James Gregor and Leibniz at about the same time, 1671 and 1674. And notice that this is actually a little bit simpler to look at. Pi was equal to 4 divided by 1 minus 4 divided by 3 plus 4 divided by 5 minus 4 divided by 7 plus 4 divided by 9. So the signs alternate and the denominator increases by 2 each time. So let's go down this pattern and see what we get. So starting out with, we get 4 minus 4 divided by 3 plus 4 divided by 5 minus 4 divided by 7 plus 4 divided by 9 minus 4 divided by 11 plus 4 divided by 13 minus 4 divided by 15 plus 4 divided by 17 minus 4 divided by 19, and do one more, plus 4 divided by 21. And what do we get? Well, we get, so I'm going to do one more, 4 divided by 21, and that equals 3.23. So notice, even though it's relatively easy to calculate, even without calculators, it doesn't nearly get you the value that you get from this calculation right there. So this is actually a much better series. How about this series right here? Let's give that a try. So to make it easier, so this is equal to 3 plus 4 divided by, that's 8 times 3, which is 24, minus 4 divided by, that's 20 times 6, which is 120, plus 4 divided by, 6 times 8 is 48, so that's 48 times 7, which is 336, and then minus 4 times, that's 72 times 10, which is 720. Let's see how well this series does, and notice that was invented by Nilakanta in the 15th century. Quite impressive. So let's go ahead and try that. So 3 plus 4 divided by 24. And again, put on my glasses, I'm less likely to make mistakes that way. Minus 4 divided by 120. Plus 4 divided by 336. And minus 4 divided by 720. And there I get a value of 3.139. Or round it off because it's 1397. So really this is equal to 3.14. And notice with just a few terms, it already converges very close to the actual value of pi. So notice that for thousands of years, people have come up with methods to try and calculate this very important number, this very important constant. It's difficult because it's a non-repeating decimal. It goes on forever, always changing numbers. But some very clever mathematical series has enabled us to come up with a very accurate value for the number pi. And that's how they did it many hundreds of years ago.